So it's been a while since I talked about ampacity corrections on the page, and ever since I posted up my conduit fill video a couple weeks ago, I've had several people reach out and ask about it, so here we go. If you're an apprentice, pay attention. So to put it in the simplest way possible, ampacity means how much current can a conductor carry. If you want the real definition, you can find it here in Article 100. You can find the ampacities of different conductor sizes in NEC Table 310.16. Now there are a couple of cases where we have to decrease the ampacities on this table by doing what's called a derate. And that's anytime the ambient temperature of the environment is greater than 86 degrees Fahrenheit or 30 degrees Celsius, or anytime we have more than 3 current carrying conductors in a conduit. And if you take a look at NEC Table 310.15b11, you'll see what the D rates are for different ambient temperatures in the environment. And if you flip on over to NEC Table 310.15c1, you'll see what the D rates are for different numbers of current carrying conductors in a conduit. So let's say we're trying to install 7 number 12 THHN conductors in a conduit where the ambient temperature of the environment is 133 degrees Fahrenheit. First thing we need to do is go to Table 310.16 and find our starting ampacity. THHN is 90 degrees C rated. Number 12 is good for 30 amps. Next, we need to find our D rate for ambient temperature. So you're going to go to NEC Table 310.15b11. You're going to find the range that 133 degrees Fahrenheit falls under, and that's going to be the 132 to 140. Paying on over to the 90 degree column, it's a 71% D rate. So times 0.71. And then you're going to bust out the math doer 5,000. 30 times 0.71 equals 21.3. Now we need to derate for the number of current carrying conductors in a conduit. In this case, it's 7 conductors. So you're going to go to Table 310.15c1. 7 to 9 current carrying conductors is a 70% D rate. So we're going to take our 21.3 times 0.7. We'll get the math doer 5,000 back out. Times 0.7 equals 14.91. Now, in a real-life application, we would absolutely be upsizing the conductors. I just chose random numbers to show you how the math works. Anyways, hopefully this makes a little bit more sense. If you guys have any more questions, you can always DM me or drop it down in the comments below.